Good morning and welcome to another episode of Talk on the Rocks. It is Memorial Day, May 25th, 2026. um, I wanted to re-record this particular lecture. This was part two of my Hawaiian volcanism. Uh, I might even add in the fact I haven't recorded for about 5 or 6 months, which is unusual for me, at least at this point in my life. But I have been very busy, and I don't want to go writer's block, but I'm trying to work out a couple of different lectures that I want to do. One being the chain of lakes up in northern Maine, and the other being the Adirondack Mountains of New York. Both are somewhat related, so doing one will help me with the other. But I have not put that together yet. It is in the works, and it's slowly coming together. In any case, the reason I chose to redo this one is because uh, as I've watched it a bunch of times, I had to keep watching it because it just seemed to fall apart in a couple places. And it's, uh, you know, not really, out of the question for that to happen when considering the subject matter of this. I felt that part one was the hardest and the most difficult to do with the geochemistry, but as it turned out, taking all that geochemistry and actually applying it to the various stages, I just seemed to end up working myself into the weeds, and I could not, at least in my opinion, explain it coherently even to myself. And I noticed a few mistakes in there. So, you know, I gave it a chance. I looked at it, I went over and over it, and I just am not happy with it. So here we are on Memorial Day. It's pouring rain out. It is in the 50s, which is, relatively unusual for this time of year. We've had a couple of hot days, and my backyard now looks like Vietnam, but we have still had some lingering cold snaps. Um, One may have even killed a fruit tree that I just planted, which I'm bummed about. But um, we had a very, very cold winter, the coldest I can remember, at least since I've lived here in this last 7 years in Alfred. But I am from Maine, and I don't recall, really seeing one that gnarly. It was below zero, probably about 13 times, which is, unheard of, really. But anyways, it's we're coming out of it. Summer's pretty much here, and we're excited for that, and gonna plant some stuff and grow some stuff. But anyway, so um, this particular lecture is going through the stages of Hawaiian volcanism. We go through the pre, the mid, the post, the erosion, and then the rejuvenation stage, and then not listed on here is the final, ending to the uh, the volcanic island, which eventually goes back under the water due to isostatic sinking because of the weight on the crust, and then eventually it gets brought up to somewhere near Alaska or the Aleutians, and it either accretes onto the side of the continent near the Bering Sea, or it gets dragged down back into the crust, back down into the mantle as the plate subducts. It's probably a bit of combination of both. So um, it is an incredible journey to really see and understand what happens to a Hawaiian island from birth, inception to death, the accretion and subduction. It's safe to say that it takes about probably 35 to 50 million years for that thing to disappear completely. I can't remember exactly what the date is on Midway. I want to say like 30 million years or so. That's the number that just comes to mind. I think that the Big Bend in the Pacific Plate was around 48 million years. So then you have another, probably maybe up to 80 before it actually gets subducted. So, but by the time you're in the Emperor Seamounts, they are just that. They are seamounts. They are no longer above the surface of the water. So They still exist, they're just not visible to the eye above water. So anyway, let's take a look at this. We're going to try to simplify it. I'm going to try not to trip over myself, try not to uh, get in the weeds and uh, stump myself as much as possible. So you may see me take some deep breaths, and I need to really think this through because I want this to be coherent. This is a really important piece of the puzzle to understanding Hawaiian volcanism. So anyway, here we go. Pre-shield stage, this is a submarine stage. This is when the volcano, basically the plume, decides to erode it becomes hot enough to start to melt the crust above the mantle. And as it does, it generates melts. The melts begin to become buoyant, and they begin to force themselves up into the crust further, thus making more conduits, more paths, and eventually it breaks through the crust, and then it becomes a surface eruption on the floor of the ocean, producing pillow basalts. The only volcano that we have that we can, really see that's been in this stage is Loihi, which is about 3,000 feet below the surface of off of Kilauea to the southeast. It in itself is a fairly giant mound in itself. It's, I think around 200,000 years old. And one of the interesting things about pre-shield lavas is they are alkalic because, of course, we're touching the periphery of the plume as we approach it. We are not into main throat stage, so we're producing alkalic lavas that tend to be found on the periphery, the cooler parts of the actual plume. What will happen is this plume will just the conduit will become more and more dragged over the main plume, and obviously a hotter part and with more fluid, the more magma, and then the conduit becomes, very, very bored out, and then eventually you're just getting eruptions that are nearly continuous for the next, probably 200,000 to 300,000 years, while the volcano builds up the bulk of its mass. But prior to that, you have an underwater seamount that struggles and fights its way to the surface, and then really fights when it breaks, and then it eventually builds up the solid structure, and then the main part of the volcano, the subaerial part, begins to grow. So Loihi is likely passed through the pre-shield stage. It is likely entering close to the main shield stage. I think we decided that it had, at least the early stages of it. In about, I think we guessed something along the order of 50,000 years, it should break the surface of the ocean and create the next island off of the coast of Kilauea, which will probably eventually build up big enough so that it will connect to the big island and produce the seventh volcano that makes up the big island. Again, typical lavas produced are alkalic basalts. And another interesting thing about these pre-shield stage eruptions is that they, I added extra time, I think I spoke about this, to the ages of the volcanoes, because the volcanoes, just like they die, the end of the volcanism is slow, I would expect that likely the beginning of it is too. Because you need to, the eruptions are infrequent, they're spread apart, they may take lots of time, but they are gaining time as you get closer to the hotspot. So it takes time to build up a mound that you can break through the surface. I mean, the ocean is a brutal and destructive, probably the most destructive force on this planet. It generates the storms. It's even the deep structure of the ocean. Although it's calm, you still get collapses and landslides, and you have chemical breakdown of water, percolating through the mountain. So it's a fight, and it's a fight that eventually it wins for a while, but then you lose. So anyway, that's the pre-shield stage, and it's not far off for me to speculate that there is a possibility that there's another one out there. Southeast of Loihi. Take the distance of the caldera of Kilauea, and then measure that distance to the summit of Loihi, and then go out that same distance somewhere off southeast of Loihi, there probably is something else trying to work its way up through the crust. Whether or not it has, I don't know. I haven't spoken to anybody about this. I haven't even, really suggested it to anybody. No one suggested it to me, but it seems weird to me that you just have this, you go from Kilauea to Loihi to nothing. It seems to me there should be something out there that's trying to punch through for the next volcano, but that remains neither here nor there. Neither here or there. But it is a possibility, and if someday down the future we figure it out, and oh yeah, there is another one. Well, remember we hit it first. All right, so about 200,000 years of that, less than 5% of the volcano, which ends up probably getting sunken into the crust, a good portion of that. We move on to the main shield building stage. This is a submarine to subaerial stage. This is when 95% of the volcano builds. Again, typical length is around 200,000 years, but we have seen volcanoes that do not go into the post-shield stage. Lanai and Oahu, the Kolau volcano, both appear to have not erupted any post-shield lavas. And given their age, they have been they produce main shield building lavas, tholeiitic lavas, for close to 2 million years. That's probably a bit of a stretch. I'm going to say, we'll say maybe a million and a half. I don't know. But in any case, we do not see any post-shield. So it's not that the volcano didn't evolve. It's just that the lavas that are being produced by the volcano have not evolved past the tholeiitic stage. In other words, it's still producing main shield stage, and it's a chemistry. It's you consider a tholeiitic shield shield building lavas. It's a chemical thing where the conduit produces, because it's so hot and so active, it really draws a lot of volume of magma from deep sources. So it's it's almost in a sense very homogeneous, in the sense that it's very fluid. It's got a good amount of silica in it, even though it is a basaltic rock. You're just tapping, the heaviest area. It's the hottest, and it creates a conduit that is just very easy for this. So when I say that the volcanoes, that the length could be up to 2 million, that's really, not what I'm saying. What I'm saying is that the the chemistry of the lavas has not switched, and there's many reasons for that. The deep plume source that injects, that produces the magma for the plume, typically gets injections, from either ambient mantle or or if you're on the lower trend, you're looking at, some recycled crust, recycled sediments that are as old as possibly 3 billion years from old supercontinents. And then these plumes have a tendency, sometimes they themselves have changed in their chemistry. So if you get a volcano like Kolau or Lanai, and and you were producing a lot of tholeiitic lavas, and then all of a sudden a new massive injection comes into it, that's mostly still tholeiitic, you're going to keep producing them, even though you're waning off the hotspot. And you may never produce alkalic lavas. You may just, the conduit or the volcano itself just may not be conducive for producing evolved lavas. In the sense, you get the main shield building stage, and then it dies. But you can't. Can we really say they're dead? Because Lanai, is not that eroded. It still has its basic shape. You look at mountains like volcanoes like Niihau, they produced rejuvenated eruptions, within the last million years, maybe even the last 500,000 years, most likely. So, and that volcano is about 5 million years old, more than twice the age of Lanai and twice the age of Kolau. So it's very possible that you are going to get future eruptions. It just you may skip the post-shield stage. The Ko'olau volcano did exactly that. As far as we can tell, there's no post-shield lava. We see two different types of, you have a main shield stage, but then you have a main shield stage evolved lava, um, which again to me suggests a possibility that we had a new injection from the deep mantle plume. But Lanai so far, and we can see that it's mostly, you can see mostly the original shape, and there just isn't any post-erosional lavas. But then again, have we really scoured it? It's one of the least studied of the islands, so we may have secrets that we don't even know about yet. So anyway, main shield building stage is very typical for producing tholeiitic lavas. And the volcano generally spends about 200,000 years over the hotspot, and then it moves away. But again, you can have volcanoes that produce the same amount of lavas for close to 2 million years and not evolve out of the actual tholeiitic stage. All right, so now we come to the post-shield stage. By the way, if you want to think of a main shield building stage volcanoes, I offer you Mauna Loa and Kilauea because they are exactly that. They are in their main shield building stage. They erupt well, Mauna Loa is on like 25-year intervals. It just went through a fairly dormant stage in my lifetime from about 80, I think it was 84 to 2024, 25, something like that. I mean, long time. Usually it erupts like every 3 or 4 years. And now Kilauea just has been bombing since 1983. It just doesn't stop. I mean, you definitely have some hiatuses. They don't last very long. So Kilauea is really just like if you were going to look at a man or per human being, you might put Kilauea at about 20, 25 years old, maybe even upper teens, whereas Mauna Loa is, it's in its late 30s, still, spitting fire and piss and vinegar. And then you look at Mauna Kea and you would say, all right, well that's a 60, that's in its late 50s, early 60s. Kohala's in its 60s, so on. But eventually that volcano is going to move over past the hot spot, and you're going to go into a cooler zone, and the conduits are going to start to freeze up. They're not going to remain as liquid and as open. There's going to be minerals beginning to precipitate out and change the chemistry of the lavas that are left over, the residual magmas. And those conduits are going to begin to start to close up and pinch. And as they do, they start to produce different lavas. And as a matter of fact, even more so, a post-shield volcano may actually, well, I'm going to say that during the shield stage, you may have numerous chambers, magma chambers, where the mixing occurs. And we know that, the rule of thumb is that there's likely one down near the base, and then there's one somewhere up in the volcano, 1 to 2 kilometers down. And once you go into the post-shield stage, it is that upper one that seems to begin to solidify first, and for obvious reasons, it's cooler. It's out of the crust of the Earth. It's so unless it's being replenished consistently, it is going to start to differentiate and start sealing up. So we see this. Two volcanoes in particular have shown that this is likely what happens. Mauna Kea, for about 150,000 years, produced a certain type of, like Hawaii, I think it was, which was, we sort of feel that that was coming from the upper level magma chamber as it was beginning to solidify and cool and, chemically, and the mineral, basically what we call it is crystal fractionation. You start cooling it down, iron-rich stuff comes out first, and then then you go down the line of the igneous mineral scale, temperatures. There's a whole sequence there, Bohn's reaction series, I believe. And that happens because you're not replenishing the upper chamber. However, the lower chamber still seems to remain active. So what had happened is around 65,000 years ago, Mauna Kea's chemistry, the magma chemistry changed significantly. And we think that was a point when you were really now just drawing eruptions from a deeper source. They had attended, like the early post shields are kind of all over the summit. It looks like they punched up through the old caldera. Yet when you go to the my phone's ringing. Sorry. So at 65,000 years ago, the chemistry of the magmas changed within the Mauna Kea volcano, and we think it was coming from a much deeper source, and hence the upper chamber may have become somewhat inaccessible or just wasn't conducive for producing eruptions anymore. We also see this in the Haleakala volcano. We think that we had a period of time where you had upper level post shields popping out, and then at some point you lost the upper level magma chamber, and everything became was coming up from much deeper source, 20, 30 kilometers below. Typical length for post shield is usually 200,000, 300,000 years, but Haleakala has shown us that it has produced post shields for close to 900,000. So post shield does not follow a real discernible pattern. We just know that it shows up. Sometimes the volcano will go right immediately to it, where there isn't much of a gap in time. Other times there'll be a large gap, and you'll see, like West Maui, I believe, shows that you have a large gap in time where you have soils horizons that were created, and then all of a sudden activity resumes. So it might go right into it. It might take some time and then start up again. It's just really up to the volcano which way that's going to go. And generally, these post shields lavas produce a subaerial cap. Again, Mauna Kea and Haleakala are your best examples of this happening. You can see it. So now, lavas produced by this stage are generally alkalic, which means they've been somewhat contaminated by crust or the surrounding lavas of the chamber, or the rocks of the chamber. Crystal differentiation or fractionation occur, and generally we have you don't produce the tholeiitic basalts. They can still be produced, but you have a tendency to have alkalics, Hawaiiites, bemerites, andesites, which is very rare, and mugurites. I'm not sure if I pronounced that right. That's a hard word to pronounce. But these are all very common in post shield, and they're just telling us that the lavas are cooling. They are coming from a source that's beginning to tap out, and they are also sitting around for a while in the chambers, thus being contaminated. Whereas the shield, they don't sit around, they just go right up and through, so they don't have a chance to be contaminated by sitting in a chamber of old magmas. All right, so once you go through that, you go into what we call the erosional gap, or the erosional stage. And this is a subaerial to submarine stage. And in this particular point, we start producing barrier reefs. There's a lot of offshore landslides. The volcano is essentially, it's unstable during most of the shield building stage, and even part of the post-shield stage, because it has so much weight. It is just massive. And as it flows out to the sides, you think that it just slopes off very gently underwater. It generally does not. Younger volcanoes are very steep and very unsupported underwater. And the way the volcanoes get their classic, nice, smooth offshore contour is when they collapse. And we have evidence of gigantic, catastrophic collapses of the volcanoes. Ko'olau is probably the most famous. You have a slide off the east side that we think moved up to a third, maybe even a half of the mountain at one shot. I mean, how do you get a block the size of Manhattan 100 miles offshore that clearly was once on the side of Oahu? Well, you need to have a lot of momentum. And when these go, let me tell you, it is got to be one of the most catastrophic things you could ever imagine, to have the whole side of a mountain go. And I mean, when that collapsed, there is the tsunami that would have been produced on the local islands to the east would have just been unimaginable. 500, 600 feet, maybe 1,000 feet in height in some places. We know that, and I know this for a fact because I did field camp over there, parts of it anyways. Actually, this was said strats, I think. But anyways, we went and mapped part of a gully that's close to 1,000 feet up on Molokai, And guess what? Tons of tsunami deposits. That's the only way to explain how these rocks that we see in this gully, rounded. I mean, everything you could throw in there, but you can tell that it was just thrown there, which is very classic of the tsunami. Tsunamis have very, very distinct telltale signs of deposits when they're laid down, and we know that that was caused by a giant. And you go back thousands of years, Molokai was only higher up, so there's a chance that was even 1,000 feet higher when this occurred. So we don't know. And Molokai, of course, the whole Molokai looks like a peanut now, but it wasn't. It used to be much more rounded, and the whole north side of it's gone. It's just gone. And that also collapsed in a catastrophically. And you can see, you look at a Google map of the ocean floor, and you can see both of these landslides that occurred. We know that they occurred on Kauai. We know they occurred on Lanai. We know that they occurred on Niihau. The west side of Oahu has a huge slump. Just half the mountain just of the Waianae just slumping down slowly, so they can be slow to be quick. On the younger islands, they always said, don't go out on a platform that has magma coming out from it anywhere near it. Here's why. Because when the magma comes out of the side of the Kilauea cliffs and it just drops, it's not dropping into anything. It's dropping into like water that's, don't go far, you're 10,000 feet down. Well, guess what? Those things collapse. Huge chunks of it just drop without any warning, and you are awarded a free trip to the bottom of the ocean, and you will not survive. You will not be found. You will be a legend and a whisper that somebody talks about when they want to tell you about the most horrifying things that can happen to a human being, because that's what would happen. So it's going to happen. The big chunk of Kilauea will collapse. It may not be in our lifetimes or from the next 10,000 years, but it's going to happen. And even more frightening, and this is from just me, Haleakala does not show many signs of collapse. And over time, the southeast coast of Haleakala has been getting more and more weight put on it, because as the big island grows, it presses down and it actually tilts the entire island of Maui towards the southeast, and it's putting the weight of that mountain on a very, very unstable shoreline of the southeast coast of Haleakala. Well, let me tell you, that is going to go, and it's going to probably take a third of that mountain with it when it does, the real one. And the wave that will be created, that's going to be marching over to the Big Island on the Kahala coast and the Kona coast, is going to be nothing short of catastrophic. You wouldn't have much. If it happened today, I would say you got, I don't know, wave travels 500 miles an hour. I think it's something like 30 miles across the I put it this way, your best bet, if you had a chance, you probably would hear it. There'd be a low rumbling, and you'd see a massive plume of clouds of dust come up. But you might have 10 minutes to get miles up that shoreline to a safe. And I don't know what would be considered safe. A third of that mountain goes, shit. You might get a run up that goes close to up to Waimea. Who the hell knows? I mean, you might, put it this way, I just don't think that you can make it. I think that you may as well just go out in the water and just swim towards it, because I don't think you're going to make it, no matter how quickly you move. Yeah, maybe you can go 80, 90, 100 miles an hour, whatever, as fast as you can go up the road. You might make it, I don't know, but it's going to be bad. And that whole coastline is gone. Like, there'll just be nothing left. It will be uninhabitable for years. The whole town of Kailua Kona will be gone. Their main port of Kauai would be gone. I mean, all those resorts gone. And that wave is going to wrap around the island and probably converge in Hilo and take that out too. And then, something of that magnitude is going to wrap around other islands. So it's bad news. And it would basically reshape Hawaii as we know it for hundreds of years. All right, so erosional gap, barrier reef formation. Think of the east side of Oahu, the beautiful Kailua side, and Waimanalo, and all those reefs. You get that. You generally lose close to half, maybe more, of the volcano during this stage. It erodes off and deposits itself and makes a skirt around the island. Through just everyday erosion, floods, storms, of course, massive offshore landslides and slumps, and of course the volcano was also isostatically sinking into the crust. Over time, the weight wants to balance, and as long as that mountain is, heavy enough to press the crust, it's going to keep going till it equilibrates. All right, so now there's islands that stop at this point. This is it. You end up, this is the end of the site, the end of the road, and you just basically erode off into the sunset, and then you become submerged, and you become a Goyut. Now, a lot of these islands go through a next stage, and that is the rejuvenation stage. And the rejuvenation stage is an aerial to submarine stage. The typical length of a rejuvenation stage volcanism it varies massively. It could be less than 50,000 years. It could be greater than 2 million. It's responsible for less than 3% of the volcano, and it can be as little as a few eruptions within less than 100 years, maybe to millions of years. We look at the time of, I think it's 1.5 to close to 2 for Kauai in Ihau that this has been going on. Oahu's about 1 million. West Maui has, I think, 4 eruptions or so called the Lahaina series. And we don't think that they were more, they were a fairly close group together. I don't think they're more than 100,000 years apart, maybe 200,000, I can't remember. But they're very close, and that might be it. We haven't had anything go on there for the last 320,000 years, so maybe, but I doubt it. I think there just needs to take more weight off. Rejuvenation stage volcanism is, for what we can tell, very, very linked to other islands up the chain. In other words, you need to build a massive island someplace upstream in order to slightly lift the island, the older island downstream, in order to initiate decompressional melting. That seems to be the key. So in other words, we think most of the action on Oahu has been related to the building of the Big Island, whereas we think most of the action on Kauai is related to the building of the Maui Nui, which is all the islands of Maui, West Maui, Molokai, East-West Molokai, Lanai, and Koho'awe. When they were in their prime, they were all connected, kind of like the Big Island, and they were enough to lift up and flex the crust underneath Kauai, we think. And later on, when I'm describing this in more detail, you can actually see the gaps and the distances and how they almost exactly line up for rejuvenation stage related to a much larger, newer island upstream. Now, this is where it gets funky, is that these are also very deep source lavas. They do not, by the time you've gotten to here, there is no upper magma chamber. It's gone. It may even be eroded and gone. If there is a lower one, it may tap it, most likely not. Seems to come from a different source. So you rarely get any matching to old conduits or anything doing with the previous main shield stage or post-shield stage, because all of these have either collapsed, they've solidified. There's a different chamber that's probably generating these. We think it's right down at the base of the right where the mantle and the lithosphere are touching, or where they meet. Which is different than the main shield stage and obviously the mantle hotspot. And then due to the depths and the sources of these, we end up having silica undersaturated magmas, which means that there's no quartz in these. They generally, you have phodite, melilite, nephelinite, basanite. You do have some alkalic basalts and Hawaiiites. These are evolved lavas, and then where the silica would normally have gone, they're replaced by these other minerals, nepheline, melilite, what have you, and so it changes basically the chemistry of these magmas. We know that they're deep source. We think they come up pretty quick, and they often do not follow any of the old conduits. So they are a mystery, and they are truly the enigma of the Hawaiian Island. The rejuvenation stage is my favorite because we've all been trying to figure this out. And some of the highest people in the world that do the most work on this my question was asked, what do we know about this at this point? I went to school in Hawaii 30 years ago, and you know, some of the guys I was being taught by were working on this, and 30 years later I asked them, and they're like, well, truth is we don't know. All right, well, that's an acceptable answer. You know, sometimes we don't know, and we're still trying to figure it out. So, anyways, that's an overview of Hawaiian volcanism. All right, so pre-shield stage. Typical length around 200,000 years, responsible for about less than 5% of the structure. It's, you know, you have this from the base to, you know, and it basically, you know, the volcano remains underwater for most of this time, if not all of it. And it's, you know, it's basically when the lithosphere, or the hot spot rather, the lithosphere finally is coming over the peripheral of the mantle plume, the outer periphery of it, where you have cooler magmas, you have less frequent eruptions, you have a melting zone that's fairly deep, and it works its way up through the crust. And that's why I put this right here. But again, you're tapping the outer part. You're not getting into the main conduit stage. So your lavas are alkalic basalts, whites, mourites. They tend not to be as contaminated with ocean crust as evidence for the 3 to 4 rate. Now, helium 3 to 4 is an interesting thing. They're primordial. Helium 3, I believe, is a primordial has a primordial source within the core, and we use this 3 to 4 ratio to kind of give you an idea of where it's coming from. And what we've noticed is that helium 3 to 4 is much. You have a tendency to have it higher in the pre-shield lavas, but not the post-shield lavas. And there's a kind of a reason for that. And it has something to do with the initial melts created when you're trying to punch up through the crust. So the volcano is thought to move past this stage prior to reaching sea level and thus entering the main shield stage. So at least Moihi is out of the pre-shield stage. We think it's entering the main shield stage. So that's, you know, that statement stands to be true. So why the 3 to 4 ratio boost? So we think this has something to do with displaced carbonatite melts, and you know, it's just a certain type of magma or rock derivative of it rather, and these contain that helium. And because the helium is less dense, or actually the carbonatites themselves, the melts are less dense. They have a tendency to pile up, almost like if you were to plow along. If this was a snow plow, you know, instead of taking this arrow going this way, take the arrow and go that way. It'd make more sense. You melt stuff here, and then because some of it's lighter, it has a tendency to pile up right in here. And that is why we see a boost in the 3 to 4 ratios. And the reason why I say that is because this is the one thing, or probably one of the many things, that distinguish pre-shield lavas from post-shield lavas. For some reason, once you've done this, the carbonatite is exhausted and it does not show up over here. And these tend to be more like orbs, or morbs rather, mid-ocean ridge basalts. Whereas over here, they are literally the same thing. They just have much more primordial helium in them. So the helium, the carbonatite melts, they cause them to be displaced because as the center plume rises, they are less dense, and they have a tendency to move ahead and work their way up and tend to pile up right in this area right here. This displacement can lead to the separation of the helium, which is thought to be partitioned into carbonatite melt, and that's away from the plume conduit. This explains why some of the 3 to 4 ratios characteristic of plume materials are found at the plume's periphery, while others near the center show a decrease. In other words, because this is one of the first things to melt and to be generated, and because it's light, it has a tendency to separate and escape first. It's almost like steam, you know, from boiling water. The steam is, you know, is the first thing to pop out, so it disperses. Instead of having an open chimney to go up, you just have it's basically blocked by the lithosphere and it piles up in the front. So that's the best way to think about it. So pre-shield stage, close to 200,000 years. It's the initial. It's when the magmas break through the crust and they start to gain momentum. And as this volcano starts to move towards the main shield stage, it will go over the mantle plume, the hottest area of it, and things will start to get much more vigorous. So more on the 3 to 4 ratios. And again, I thank Dr. Mike Garcia for pointing this out to me. I did not know this, but I mean, he's the guy, he's the man. So 3 to 4, helium-3, helium-4. High relative abundance of primordial helium-3 are commonly found in ocean island basaltoids. They are thought to be derived from mantle plumes, and high 3 to 4 ratio have been used to distinguish plume type from non-plume type. In simple plume models, one expects to find the highest 3 to 4 ratios basically in the center of the conduit. This is not true, which is sampled during the main shield building stage. However, the actual locus of the highest 3 to 4 ratios is sometimes significantly displaced, where I'm saying it's displaced up here. This is best documented for the Hawaiian plume, where the highest 3 to 4 helium and basalts are found on Loihi, a volcano tens of kilometers ahead of the inferred plume center. And this is what this is depicting. Here's Loihi, this would be Kilauea, Mauna Loa, so forth. This is the main plume. This is where you have helium-bearing carbonatite, and then you have peridotite over here that's carbonated, but this has been exhausted. For whatever reason, this is on its initial trajectory. It melts ahead of time. It's light. It piles up right here, and we see it. We see that the pre-shield lavas have a tendency to tap it and bring it up, and then once it's tapped, it tends to be exhausted, and we go back to normal levels or background levels, I guess would be a better word. So helium-3 is primordial. It is generally thought to be stored in the core of the Earth. The hottest part of the plume would tap the deepest parts of the mantle core, so therefore it should be in the main part, but it's not. As I said, it's due to the melting. Because of its density, it has a tendency to build up first in the fore part of the Earth, the plume. It does not. In fact, the highest percentage of 3 to 4 are found in the pre-shield lavas. These lavas are likely interacting with carbonatite, and that's the reason why. So as this comes up, you melt the crust around it. You're bringing it up. It separates here, and then it basically gets stored in the front part, the advancing side of the plume, and then you tap it, you exhaust it, and then you move past, and then you tap into areas that have regular background 3 to 4 levels. All right, volcanoes closest to the pre-shield stage. That would be Loihi. This is it in all their glory. We're looking, yeah. Sometimes this can be confusing. This is Kilauea over here. This is Loihi. You can see there's a caldera, what looks to be a caldera. You've got the general shield stage. You've got a steeper side here, but then you have an elongated. So the rift has kind of gone along like this. This is how it's formed. This is looking at it from the west. This is coming back this way. Again, you're seeing the rift zone, what looks to be a summit area here. The piling of lavas against the pre-existing Kilauea shield. This is what they do. They overlap and they pile up. Basically, there'll be a next one will pile up over this. And then this is from the north, looking down. And what you're seeing here is you're looking at basically, so you're standing on Kilauea looking down, and you can see that Loihi is a very steep-sided volcano on each side, but on the rift zones it is not. And this is eventually going to fatten. As long as this rift zone, sometimes a rift zone can change. It may end up going this way due to this pre-existing structure, but it looks to me like this one's fairly well established, and this will eventually break through the surface. So again, the side of Kilauea, overlapping, and then you might have some slumps right here, maybe some slumps here. Looks like this could be one here. These could just be huge lava flows that erupted from the side and just came down. I mean, that's how the volcano's built. And this is an example of pre-shield, but it is now going into the early shield building stage. Main shield building stage. Typical length of this is about 200,000 years, but can occur over 1 million. And sometimes it stays that way for up to 2. It is responsible for 95% of the volcano structure. They produced tholeiitic lavas. That means that they are basically the hottest. They are the most fluid. They are the most silica rich. They are continuous. They are not contaminated. And this is when the volcano is, it's a teenager. or it's in its 20s, and it is just, like I said, it is pissing vinegar, and it is very active. And this is where Mauna Loa and Kilauea are right now. So what you're getting here is you have low velocity lavas produced. You have the highest point in partial melting in the center of the plume. Depths of melting are down to 200, 400 kilometers, but there's also chamber probably here of magma mixing, and then an upper low in here. It may even be one up inside the volcano somewhere too, but these are just zones of melting, and again, the real deep source down here. It's generally more than two areas of melting or mixing. Shallow magma mixing chambers may be present. It has the lowest amount of crustal contamination, often contains the highest amount of recycled crust within the plume. So when I say this, this is essentially saying that we think that the plume, and I think I described this in lecture 1, is generated at a contact boundary between the ambient mantle and what we refer to as a slab graveyard. In other words, pre-existing supercontinents, and in this particular case, this would be Rodinia. Pangaea was about 300 million, but Rodinia was about 9. When Rodinia was created, a bunch of oceanic slabs went under it, and they piled in the south. Right now, they're pretty much down around the South Pacific, sort of near between, say, like Hawaii down to like New Zealand, Papua New Guinea, near Australia. That whole area we think is, a slab graveyard. And then the northeastern periphery of that, where it goes, where it stops and you go into ambient mantle, is where we get the Hawaii plume. And it taps into, some of it taps ambient mantle, some of it taps old recycled crust. And we know that from the geochemistry of the volcanoes. And there's two types. There's a Loa type and a Kea type, which I went over. The Kea has a tendency to be more homogeneous and produce ambient mantle eruptions. It's, I believe it's more evolved. I can't remember. And then the recycled crust has a tendency to be more contaminated, has higher strontium ratings, and it's less primitive. I think that's how it goes. So anyways, at this point, you're tapping into, if we do have recycled crust melts in there, it is dragging them up at this point, more so than any other point in the volcano's life. They often contain the highest amounts of oceanic crust within the plume. Again, recycled crust is the result of subducting oceanic slabs from other supercontinents. And there may be shallow magma chambers 1 to 2 kilometers within the volcanic edifice itself. So that's a good summary of main shield stage. And this is what makes the bulk of the volcano. Main shield stage continued. During the tholeiitic main shield stage of Hawaiian volcanism, melting primarily occurs at depths between 5 and 4 GPa, gigapascals, which translate to 150 kilometers, 93 to 75. Now, this is the melting of the actual mixing of the lavas that are produced for the volcano, not the deep source. The deep source is a different, that's a different melting area. That has to do with the actual slabs. It has to do with it's initial melting. This is where you have mixing, and when you come up, because you're under such great pressure, this is where once you've created some sort of a diapir or plume that's coming up, then you get real mixing when you get up to about 93 to 75 miles up. This is where the parental melts for shield building lavas are produced. They melt, and then they pond in a magma reservoir at about 70 kilometers before erupting. Here's the breakdown. Initial melting. The tholeiitic magmas, which are volumetrically dominant during the shield stage, are generated by melting in the mantle at depths between 150 to 120 kilometers, 5 to 4 gigapascals. After melting, the magma accumulates and ponds in reservoirs situated at a shallower depth around 43 miles before erupting. The melting process involves the Hawaiian plume, which is a plume of hot mantle material from deep within the core. Studies using melt inclusions in trace element analysis suggest that the plume may contain a component of recycled eclogite that melts at depths greater than 100. That's eclogite is produced associated with recycled crust. While the primary melting occurs at depths mentioned above, there can be some variation depending on the specific volcano and stage of evolution. For example, Some studies suggest that melting depths of 200 to 400 kilometers are more appropriate for Hawaiian basalts compared to other volcanoes like the East Pacific rise. Now, the post-shield changes as the Hawaiian volcanoes transition from shield to the post-shield stage. Magma storage depths can shift. Shallow reservoirs may become less prominent, while deeper reservoirs persist. And this is all according to the USGS publications. Here is Mauna Loa in all her glory. I mean, it's almost as if you're standing on it. You're not really quite sure you're standing on something because it's, you're standing here. You can't even see the summit. In fact, we can't even see the summit. You're close to seeing it, but not entirely. Mauna Loa has been produced with, massive amounts of outpouring of fluid lavas, hence the very broad dome shape. Once they start going into post-shield, things will start getting thicker, more like putty, and they'll start, and more explosive, and they'll start producing big cinder cones and a much steeper profile. Here is a magmatic plumbing system for the, something like Kilauea and Mauna Loa. You have basically a very deep melting zone right here that's feeding both of these reservoirs. Again, this is not definite. I mean, this is just a very simple. There's probably all sorts of stuff going on under here, and these are probably not similar in size. It's hard for me to tell really what the true what's the word I'm looking for? Without true seismic information, you cannot tell what is really going on under these. And if you do seismic analysis, you'll see that the S waves will show where these reservoirs are because they don't travel through liquids the same way they do through solids. I mean, this is a very old and accepted technique. And my guess is that you would find that this one's probably a little higher up than this one. And as this grows, it might even begin to eat away and move higher up. And there's probably something down here. And of course, you have the very deep source plume down here where you have, melting generated here. So these both have rift zones. So you'll come up into a summit reservoir and then you'll push. If you're not going to pop through here, you might go downstream a little bit or downstream here. These are very well-defined conduits. They usually roughly 180 degrees opposed to each other. Mauna Loa has the same thing. Kilauea has it. The Southwest Rift Zone is, seems to be less active than the East Rift Zone, and there's probably a good reason for that because as this continues to build, it's pinching on this. All this mountain wants to do is move this way because it's so heavy, it just wants to push everything out. Whereas over here, you don't have the weight of Mauna Loa pushing on it. So this one over time has begun to really grow exponentially in reference to this. And my guess is that, over time, this could even shut off. Who knows? But I think Mauna Loa has reached its zenith, and I don't think it's going to get much bigger. So, the fact that what's happening is that this will still erupt periodically, but it's just going to keep pushing the unstable southeastern side of Kilauea out, and it eventually will collapse. All right, here is a cross section of the plume. This is kind of giving you an idea of what's going on. You have eclogite down here being brought up. You have melting going on here. You have carbonate melt rather right along here. Probably have it over here, but that's why this piles up. I should have put this in here because you also have it over here. And what you end up happening here is that during the main shield stage, this is pulling up all of this. So you've got the CO2 bearing peridotite. It comes up in. There's a reaction right here. You have melts. And during the main shield stage, you have high nickel, high silica, low calcium, low magnesium. There's a tholeiitic melt, which is right here. And this is what's producing the shield stage. Once you've moved past this, you're going to start getting stuff from here and from here. So once you come over here, you start to have low nickel, because these are starting to differentiate out, or they're going into other minerals. You'll have low silica, low nickel, and then high calcium, high magnesium, and you have what we refer to as an alkali melt which is also contaminated, and these alkali melts have a tendency to be over here, and this is where the rejuvenation stage starts. Carbonated peridotite, basically what that is saying to you is that the peridotite is loaded with CO2, and this has a tendency to get separated and popped out, and then you'll end up finding it, it'll start showing up in some of the downstream volcanoes. I think that's how that works. Not 100% on that, but this is a really good simple diagram. So you have melting area A, and you have melting area B right here. And these are what's produced. This is what's basically produced in the shield building lavas. You go from an eclogite melt, then you end up going to a peroxenite, and then the peroxenite basically, so you have a shift right in here, and this changes the chemistry a little bit. However, once you get older or less cooler, you don't quite have that reaction as much, and so the chemistry again changes. And you move from a high silica nickel to a low silica nickel, and then you pump up your calcium and magnesium, whereas in the main shield stage they're being basically melted off. So that's sort of a simplified version of the plume. Main shield stage, eclogite right here, as we just talked about. You've got a decompression zone here. You have the throat right here. You have a melting area right here. You have eclogite segregation as it goes on. You have all sorts of stuff going on. And then you have, of course, as this goes downstream, you have the conduit punching up through, and you have another area of melting right here, and probably another one up here. And so what happens is that this comes up, it gets separated out, and then it has a tendency to pile somewhere downstream that gets tapped in later eruptions. So the main shield staining stage is just basically saying that the most hot, the most liquid, the most consistently fluid stuff will come up, and that ends up what's coming out. Kilauea magma conduits. So basically 10 kilometers down, you have the basal decollement, which is essentially saying this is where the crust, and this is ocean crust, and this is volcanic material. There's a line that separates these two, because you go from one type of material into another. So where the volcano started to build this is the floor of the ocean at one point. So you come up through, as we said, that oftentimes Kilauea will allow magma to pump up through, and then it gets shifted down the east rift zone, and we can see that with all these different Mauna Ulu, the Pau, Pu'uo'o, all of these basically are above a rift zone conduit that originates from the main conduit going up to Kilauea summit and then shifts down here. And this is, if this is clogged, blocked, or it's just a matter of which is easier. Volcanoes don't care. They're just going to pick the path of least. Sometimes this is the path of least resistance, and then sometimes this is the path of least. It just depends. Once we unloaded, and once the caldera drained and collapsed, and we removed a bunch of weight and a plug, it was very vigorous, and now it's been filling back up the caldera. And we haven't seen much action down here, but for most of the 90s and the early 2000s, all the action was here, and then it resumed back up here. We even had a little bit going on down here. Now, these can often be stacked. So, in other words, there might be another deeper rift zone that comes out. It's not necessarily just one. It could be, a bunch of them. So, this is just a generalized zone. I mean, a generalized diagram of this, but it's probably much more complex than that. And this is a map view. So you have the east rift zone going this way. You have the seismic southwest rift zone, the volcanic side. I guess these are just essentially saying that they pick up seismic activity more here than in this one. And I'm not exactly sure what the seismic southwest rift zone, the difference is. Maybe it's just a deeper source that injects this. I'm not 100%. But in this, it looks like it's significantly placed forward, southeast of the actual volcanic zone. So a little confusion there. Not sure why that is. All right, post-shield stage. As the Pacific plate migrates over the mantle plume below Hawaii, magma flux decreases, resulting in changes in eruptive volume, style, and composition. It is thought that the melt storage becomes deeper and ephemeral with the transition from highly voluminous thallitic shield stage to less voluminous alkaline post-shield and rejuvenation stage magnetism. To quantitatively test this, we applied high-precision fluid inclusion barometry via Raman spectroscopy to samples from representative volcanoes at different elevator stages. And it suggests an evolution from shield stage shallow magma storage, 1 to 2 kilometers for Kilauea, to post-shield stage that includes crustal magma storage within the volcanoes around 2 kilometers and a deeper storage below the moho about 20 to 27 kilometers for Haleakala. As I said, there's likely 2, and the upper one begins to solidify first. The rejuvenation stage, however, displays mantle-like dominated storage 20 to 30 kilometers below. High melt fluxes likely form stable conduits from the mantle to the shallow reservoir in the shield volcanoes. As flux melt decreases, the moho becomes a boundary controlling the melt. And that's from Lynn, Hawaii. And what this is, to simplify this is saying that we have a shallow stage, we have a shallow chamber in the main shield stage that progressively begins to seal up once we go into post-shield stage, and then only the deeper one generally works once the upper one begins to solidify. The lower one, because of the heat, because of the depth, and because of the ability to replenish itself, because the conduits take longer to solidify, the deeper chambers are generally what's left over for the post-shield stage. Post-shield stage, this is a subaerial. Stage for the volcano. The typical length varies hugely, and it's transitional. In other words, it can be, you go from one stage to the other, and during that time it can happen simultaneously, or it can happen with large gaps in time. Some volcanoes do it, they go right into it, others do not. So you can have a time period from 0 to 900,000 years. Haleakala has been, I wouldn't say that it would be 900,000 years for Haleakala has been in that stage for close to that. So yeah, actually that is an accurate statement. But other volcanoes go right into it. You don't see a gap in time, so that's why there's 0 to 900,000. Responsible for less than 5% of the volcano. Phaletic basalt, alkalic basalt, hyoite, and bemorite are the general lavas that you would be produced during this. They're generally more explosive, hence the large cinder cones produced during this period of time. A lower partial melting on the perimeter of the plume core. The plume core is very, very hot in the center, and you generate a large amount of melt. Whereas on the periphery, where it's not as hot, you end up getting much lower. You don't generate the volumes that you do, which is why the eruptions tend to be shorter and very far apart. Lower partial melting on the perimeter of the core is around depths of 200 to 400 kilometers. Generally no more than 2 areas are melting or mixing. Deep magma mixing chambers may be present. Shallow upper shield building stage magma chambers may become less and less recharged by fresh magma and begin to crystallize over time and finally solidify. Higher amount of crustal contamination because the lavas sit in these chambers long. When it's in the main shield stage, it just goes right through. It doesn't have time to take out pieces or assimilate pieces of this. But when it sits here for a while, it certainly does. Shallow upper shield building stage magma chambers become less and less recharged over time. Okay, I just read that. General cooling trend for magmas generated. In other words, the magmas are cooler, so the hotter minerals begin to be taken out of it. Once the upper magma chamber solidifies, primary magma is generated from deep magma sources near the mantle. In other words, this one's solidifying, this one is not. Similar to pre-shield lavas, but with less primordial helium-3 to 4. Possibly be related to the removal of carbonatite in the ocean crust during the pre-shield stage. So You got the plume. Now you're on the periphery of it. I mean, this probably like jumps right through. It's just the way they had to draw that. But you have a deep source, and this is the one that's feeding Haleakala, and this is the one that's feeding Mauna Kea. But this one here is fractionating, and it's beginning to seal up, and it's not getting, this conduit is having a harder and harder time pushing through. And eventually this is going to just seal up, and then you're going to get eruptions that sort of bow out to the sides. All right, Mauna Kea volcano, post-shield stage. This is like the textbook example of what a post-shield Hawaiian volcano. This guy, you know, he's in his upper 50s or the 60s if he was a human being. You see what was once a broad dome, but over time the dome has become steepened. You have cinder cones here. You have cinder cones all over this thing. And you have a difference, you know, and you have ash, and you have a soil horizon because this volcano has slowed down and it's erupting, and weather and time have broken down a lot of the materials. And not to mention these eruptions are much more, they produce a lot more ash, and it piles up around on the volcano, making soils. This soil right here is incredibly rich with nutrients because of this. The once lava flows have broken down, now you have, you know, meters of soils that are, you know, like dirt and stuff like that. It's not all just rock where things can grow. And a caldera was probably present somewhere up in here at various times, and then of course it was sealed over by the later stage, more viscous, explosive eruptions that, you know, when the magma comes out like putty, it doesn't travel very far, so it has a tendency to pile up and cover this cap, and it basically made this cap of post-shield lavas. That's not to say that you don't have lavas that run down the, you know, run the volcano. You can see that there's been many that run the course of the volcano down into the ocean, but they're not as common. I mean, here's a cinder cone. Here's a big one. This isn't really showing too many of them because they're kind of obscured, but they are everywhere, and they have a tendency to line up in 3 rift zones. So you got the caldera, you've got a rift zone here, and then one on the other side. Likely, that's what the rift zones were when this volcano was in its heyday. Without this all came later. And this is from the upper level, likely the upper level chamber as it began to fractionate and allow magma to become a buoyant punch through. And then later on, as this began to seal up, eruption and cinder cones began to form around the periphery of it because it wasn't as easy to punch up through this. And these later ones have a different chemistry than these. Late shield transitions to post-shield, Mauna Kea volcano. So 300,000 years ago, we got late shield stage. We got an upper chamber, you know, or storage area. We got a deep conduit. We got a nice open system right here. These would be the early shield. This is late shield. You got the crust bending down. You got the mantle. Eruptions from active reservoir fueling this. And this is, you know, this is you get the rift zones coming down here. Now you go to 150,000 years ago. This is no longer no longer one giant chamber. It's separated. It's cooling. It's moving into like pods or smaller chambers in a once much larger chamber. And we are also getting deflection of material coming up, where if these conduits aren't exactly playing ball, it might get forced into older cracks or stress fractures and start popping up into other areas. And so you have intermittent and diffuse conduit system, you have a diminished magma supply, and you have small ephemeral magma chambers and feeder dikes. In other words, this is not the main thing that we once had. It's a small relic of what was once there, and it's producing eruptions that have a tendency to pop off in different areas. Now, here's the caldera, but now notice that because these eruptions are cooler, more explosive, and less fluid, they have a tendency to pile up, and now you've got a cap on top of that. By about 70 million years ago, this upper level chamber is now gone. It is solidified, and now we are tapping basically the basal area of the volcano, and this is now a true post-shield stage, a later post-shield stage, and you're producing basaltic and Hawaiiite substages. Basaltic magma collects at base of crust due to greatly diminished supply, and this is the only place where you're still getting the heat. There's just not enough heat to keep these. And what happens is it accumulates here, and then eventually it too is not quite getting the heat. It will fractionate and become a buoyant and eventually punch through like a zit. And this is what you get now. You have no more of this upper chamber. You have magma being generated and stored down here near the base of the volcano. You have low density Hawaiian magmas that seep accumulates, and low density means that this is eventually going to find its way through, but it doesn't happen until things begin to cool down and you take out the heavier elements. And so now you just have conduits coming from the base. They don't follow the true throat of the main shield stage. They kind of make their own. So this is a main difference. This is the early post-shield stage. This is the late post-shield stage. This one shows the magma chamber beginning to solidify, and it shows deflection. Now you just have down here, and this is deflecting and making basically its own conduits and popping out. I mean, yeah, it still follows the weaknesses of the main throat, but over time this will become more and more solid, and it will start popping out around the sides. All right, erosional stage. The erosional stage is a subaerial stage. In other words, a volcano, but it could end up going into submarine. Well, no, you can't really erode anything underwater, at least not in the sense that what we would consider erosion. You have chemical breakdown. That's a whole different thing. So erosional stage. Now, once the volcano has done its thing and it's given up its goods, it's erupted most of its magma, the plume supply has cut off. You are now working on, just basically anything that's left over, and eventually you just stop. And the erosional stage is a typical, this will go from, I don't know why I put 200,000 years. I guess it's because you can go through this and then all of a sudden pop out into rejuvenation stage. But the reality is that the erosional stage goes on and on and on, but it will get erupted periodically through rejuvenated volcanism. So this is, it can be greater than this should say less than 200,000, but it can be more than 2 million. But the reality is that, the erosional period is just a period of really the end of the main phase of volcanism. The rejuvenated stage is an afterthought. So this is really signifying the end of the volcano, and the rejuvenation stage will just come in and periodically add some more material, but not enough to really to make that much of a difference. I mean, yes, there is quite a bit of it on Kauai, but again, it's nothing like the main shield stage. So typical length, it can be around 200,000, but can occur, much later. I mean, it can just keep going, and then you'll get rejuvenation, a million or so years later. It's responsible for 0% of the volcano. In fact, it's a negative. There's no eruptions, coral reef development. The island can subside 500 meters or more, can even, probably up to a mile or more. Partial melting has reduced significantly, has now moved to the base of the lithosphere. Shallow magma mixing chambers may be present, but they are now solidified, as well as the conduits. In the Hawaiian Islands, the erosional stage follows the post-shield stage and is characterized by significant weathering and erosion, leading to the formation of valleys, canyons, coastal cliffs. During this stage, coral reefs begin to grow around the subsiding volcanic islands, and in some cases, the islands may eventually erode down and become atolls or guyuts. Here's a more detailed breakdown. End of shield stage. Volcanic activity decreases during the post-shield stage, and the volcano begins to cool and subside. Erosion and weathering. As a volcano moves away from the hotspot, it is no longer supplied with fresh magma, and forces of erosion and weathering begin to dominate. Rainfall and runoff carve deep valleys and canyons into the sides of the slopes. Giant landslides can occur, reshaping the island's flanks, leaving behind debris fields on the floor. Weathering breaks down volcanic rock, contributing to the erosional processes. Reef growth and subsidence. Fringing reefs begin to grow around the eroded island as it sinks or subsides due to its own weight. As the island continues to subside, the reefs may eventually grow to form a circular atoll. If subsidence continues and the island is completely submerged, the coral reefs may die, leaving behind a flat-topped seamount known as a goyu. Now, in some cases, renewed activity, rejuvenated volcanism, occurs after a long period of erosion. These eruptions are typically smaller and less frequent than those during the shield building stage, and they may occur in different locations on the island. Rejuvenated volcanism can add new features to the landscape, such as cinder cones and lava flows. And the best example is something that we all know, and all you have to do is go to Oahu and look at Diamond Head. That is a classic rejuvenated stage volcano. Erosional stage, sort of a little diagram here. You got the pillow phase of the pre-shield. You got the proto-shield. This is the early main shield building stage. You have the when it begins to breach, an explosive stage of the shield stage. Subaerial, this is basically the bulk of the island being built up. You got the post-shield where you build the cap right here. Now you got the erosion and subsidence stage. So now the volcano's been basically stripped of a lot of stuff, and the old, you can see what looks like the old profile, but it's really not. You're seeing a ghost of it. And then you have the rejuvenated stage where you have eruptions. This is definitely based off of Oahu. You got reef, you got diamond head here, you got some flows that go on it, and this is rejuvenated, but again, it's not following anything of the original conduit. You have the coral atoll stage. These are the northwest Hawaiian Islands. Think of like Midway. You got a big lagoon. You might have a small piece of lava rock, and we have drilled some of these, and we know that the lava rock is down there. You have a central lagoon, and you have a fringing barrier reef, and then eventually you move into colder water, or the volcano just sinks too fast, and that's it. That's all she wrote. This is this is now never coming back up unless you had a massive drop in sea level, and it's going to take its ride up to the Aleutian Islands and get destroyed. Typical topography of the erosional stage. This is looking towards Waimanalo. This is Makapu'u right here. I have spent much time out here. This is where I train a lot for my body surfing. I have gone out here on days when the waves are breaking somewhere out here. It took years and years and years of confidence and swimming abilities and training to get to that point, but I got to a point where I would go out there on days when the beach was even closed, and I'd be the only one around there. I mean, just no one would do it. But that was when I found, that was when I just absolutely loved it. To get to that point where you can just handle the ocean in an 8 to 10 foot, wind swell or just storm surf. I mean, to me, it was the greatest thrill. It was never a dull moment, and it was clarity. You just always had to be paying attention. And the rides that I would get, I would take off on a wave here and just zoom through and come out right over here. And sometimes I'd go this way if it broke the right way. But this reef right here is just tailor-made for some really big body surfing. So Waimanalo here, actually Waimanalo's here and here. Kailua is up here. Marine base is somewhere down there. Actually, it's over here. And this is all a fringing reef. There used to be another side to this, but you can see how these dip away. So we know that somewhere over here there was another side that did this, that dipped this way. And this is all gone. This was collapsed. It fell off into the ocean and never to be seen or heard from again. And it produced a large, what we call a pulley, this cliff. It goes all the way around up through here. Now, when this happened, it probably was some out here, and it just eventually eroded back. But you literally lost about a third of the volcano when the Nu'uanu slide occurred. So, but this is very typical of erosional stage. You've got some old relics of the caldera in here. This could have been, I can't remember if this is just an erosional remnant. I don't think it's a cinder cone of any sort. It's just part of, the caldera in its day. This is very thick, blocky lavas of the caldera. These are more resistant. This makes up Olomana Peak. You got some cinder cones over here, and then the main caldera was somewhere out in here. This right here, I just think that these are just erosional remnants. They could have been just slightly more resistant to erosion. I don't recall there being a cinder cone right there. So, but anyway, this is a beautiful shot. Got Sea Life Park here, and another fantastic wave right here. All right, the Nu'uanu and Wailua slides. I've been talking about these, and now I'm going to show you what I'm talking about. So, as these islands began to subside and erode, the eastern and northern flank of this one became unstable, and eventually they collapsed. And when they did, they created debris fields out here that, this may even go out here, that are literally unimaginable. Which one went first? I cannot tell. I'd have to take this apart again. But in any case, you see that this volcano was probably shaped like that at one time. This volcano was probably shaped like that at one time. So all of, like, you don't get this big scallop right here uh, without, like, the volcano did not form this way. This was removed, and all of this material is here. And all of this material is here. So the whole other side of these collapsed. The number that comes to mind, I feel like, is 120,000 years, but uh, I say that with a very, very reluctance. I can't remember the exact date, how we dated these. Um, but in any case, these are massive, gargantuan landslides of the largest scale on the planet, like some of these. And, you know, over here, now let's look at the Waianae. What do you think this one looked like in its date? It was probably like that, you know? Maybe it came out here. This is the peak of it. It probably came out something like that. You have two more about here, by the way. And of course, you know, this one was probably like that. But you have another slump right here. So these things are everywhere. Everywhere. This is part of the Kauai one. You can't see Kauai, but this is debris from Kauai. But these things are unimaginably large. And when they go, all bets are off, man. It is a brutal, brutal thing to occur. And the volcanoes, almost all of these islands have some sort of these, but these are the two most well known, I believe. So at some point, this just went, and it wasn't gradual. It must have gone all at once. And it's the same thing with this. Now, the question is, and I don't think it is, but did the removal of all this weight help trigger this rejuvenated volcanism of Kalaupapa and the other ones right in here? I don't know. I know that this is about 500,000 years old, so unless this is, I think it's younger, so maybe it did not. Although that can't be, because this would have been this did come after this. This is the only way that happened, because this wouldn't be here if this collapsed. This would have been taken out with it. So obviously this popped up after this landslide, and I think the same could be said for these too. So well, however old these are, they have to be younger than this. That deserves a little looking into, because it's very unlikely that this would have happened prior to this, because I mean it's completely untouched. It would have gotten dragged off with it. So my guess is that these are both. You could date these somehow by correlating. So if this is over 500,000 years, then that would jive. Maybe it is about 500,000 years and it did trigger this. I really need to look into that. I'm thinking of 120,000 years as the one that happened off of the Big Island on Kohala. So these may be significantly older. Erase that from the, omit it from the record. I do not believe these are 120,000. These are much older, and they have to be based on both of these new cinder cones. That's my story, and I'm sticking to it. All right, rejuvenated stage volcanism. Now things get completely wonky. So we've gone through the stages. We are now down here. We've been dragged about 300 kilometers off the hot spot. We'll just call this Oahu for now. And what we have here is we have melting somewhere down in here at the base of the lithosphere, not in the crust. We have mixing chamber in this area above it that is now solidified. We have this upper one that is a long time solidified. And we have eruptions that have a tendency to be outside of the main area. Now, they can come up through here, but it was just coincidental. They are not following any of the old conduits. If you notice, this is a little more spread out. In other words, it's kind of being deflected. It's like, it's a good chance that when these come up, they get deflected around. So if these are solid, they are not going to be easy to go through. They're going to get deflected. And it makes sense because when you look at the eruptions on Oahu and Kauai, yeah, there's a couple that are in the center, but for the most part, they are on the periphery. And they have a tendency, even more so, to be dragged down on the southeast side of the islands, or the volcanoes. Kauai has that. Oahu has that. Lanai, I mean, West Maui does not, because I think that has something to do with the Haleakala on the eastern side of it. So the only rejuvenated volcanism we have on West Maui is on the western side, but again, it's off of it's outside the main mass of the shield. It's sort of on the periphery where it's lighter and probably easier for magma to punch through. Again, these are all opportunists. They're going to take the path of least resistance. So you have a drag effect on the plume. The plume gets stretched out and dragged. You have these mountains building up over the main conduit, and then they're depressing the crust. And eventually, if you get everything coming together, you're gonna lift this up just enough to take weight off of this deep area where this is sort of coagulating, and then you might initiate melting, and then you get something to punch through. Now, this drag effect of the plume is just a result of it being dragged downwind by the lithosphere. So it stretches out, and it also erodes the crust, I might add. It actually erodes it up, kind of like this. And so not only does this, so I'm going to actually change that right now. All right. Okay, I just wanted to fix that. So this plate, this oceanic crust, actually begins to erode a little bit from the heat generated by this downstream dragging of this plume, which also helps accelerate the fact that if there's less weight being pushed down on this and it's being lifted up, these two things can help combine the fact that this will eventually help whatever magma gets generated here. It will initiate more decompressional melting and punch it up through. So that was really what I was trying to. There's a bunch of things that contribute to this that have to come together, and we think that also one of the more important things is that this is 100 kilometers here, but it might be only 60 here because it's eroded and weakened over time. So that's sort of an important thing. So think of it this way: as this gets dragged down, this becomes heated, it breaks down, it begins to erode. Probably it doesn't actually really contribute much to the melt from what we can tell, but it does erode it significantly enough to allow rejuvenated lavas to be easier to punch up through the crust. So that's the main point of this slide. So main plume, periphery, melting initiated here, deep source melting, accumulating at the base of the lithosphere. Lithosphere begins to erode. This begins to move up a little. You have the weight from a huge island here that helps pop this off a little bit and lift it up even more. And, taking off just the right amount of weight and pressure will allow this to have a runaway effect of melting, and you'll end up punching this up through. And that's one of the things that helps generate rejuvenated lava. And if you don't get these things all coming together, it might explain why some islands just don't have it. Maybe you didn't get enough weight. Maybe the distance was wrong. A lot of things can come into play, but it seems that the bigger islands, Kauai and Molokai, Kauai and Oahu, have generated a good amount of rejuvenated lavas, and they seem to be very tied to the islands upstream of them. Sources of melt this is where it gets sticky, and this is where I get in the weeds, so let's try not to do it again. So you got the shield, the main conduit, which is what we were just looking at right here. We got the post shield, which is here, which is on the periphery. And then we have the rejuvenated, which is here, 300 kilometers down from the main mantle plume throat. So what we have is you have sources of materials coming up. Now here in the main melting zone, everything kind of melts, it gets pushed together, and then it comes out as as tholeiitic shields. Well, once you've moved off this throat, so this would be Mauna Loa, Kilauea, this is now Mauna Kea, your melting zones shift slightly, and your melting zone here basically is much smaller, and it's not tapping as wide of an area, so you're generating smaller lavas. Now, what's also happening here is that these conduits, this once big giant conduit, is now, basically sealing up, and you're getting veins coming up here that are not nearly as conducive for large eruptions or to allow materials, and the lavas are actually colder, and you're producing alkalics. Now, once you get down, a few hundred kilometers, your conduits are completely uh, wrecked, and anything that melts down here at the base of the lithosphere is going to have a difficult time coming up through here. But if you get enough melt generation and it's fluid enough and it's buoyant enough, it will make its way and pop out. So you have these. I guess they put in these sort of, check marked, or these what's the word I'm looking for? They're not solid lines, they're dashed lines, to represent the fact that these are not always open, and they may only be open once when they are generated by the eruption. So you've got the asthenosphere, you've got your main melting stage, which is fairly deep. Then you've got your post-shield melting stage, which is a smaller area, but once the plume is not, you're not over the main plume anymore. You're getting stuff that's basically left over and is now going to start fractionating. And then over here, you get, for rejuvenated, you have something that's moved up slightly, and now it's at the base of the lithosphere and just kind of hanging out there waiting for something to get released. So this is a schematic illustration of the plume during the 5 million year evolution of Kauai from shield to rejuvenated stage. The vertical plume stem consists of the upperlaying material from the deep mantle. Boom, we got that. The plume spreads out laterally as it rises and is dragged beneath the migrating 100-kilometer Pacific plate. Yep, dragged. The plume consists of a matrix containing the Ka element, with blobs of Ko'olau and Dm components, which I believe is depleted mantle material. The shield stage of the Kauai, incorporates Ka and Mauna Loa components with little or no depleted mantle. So right here. So it's mostly this, but a little bit. The post-shield lavas form as Kauai moved away from the vertical plume stem. Boom, it's right here. The rejuvenated volcanism occurs 300 to 400 kilometers downstream from the vertical plume stem, incorporating a greater contribution from the depleted mantle plus a mixture of Ka and Ko'olau elements. The greater proportion of depleted mantle component in the rejuvenated lavas, which are formed at low degrees of melting, suggests that this component has been recently enriched, lowering its solidus temperature. So the enrichment, which is good, I think that might even come from the enrichment lowers the temperature. Again, contributing to the fact that you release pressure, you erode this, and then you actually have material that even lowers the temperature more for melting, all contributes to the rejuvenated coming here. Like I said, there's a bunch of things that need to come together for this to actually happen. And when you get a little bit more of depleted stuff in there, and you bring in a little bit more of enrichment, you are going to lower the temperature of what needs to be melted. And again, it contributes. You don't want it to go harder to melt, you want it to be easier. Everything in here is basically moving towards making this easier to melt at lower temperatures. That's the whole key, and that requires uplift. It requires materials to pond. It requires some new chemistry to be put in there. And since most of these have like 3 different types, most rejuvenated lavas have 3 different types of sources, all of these combine to make something that will melt at a lower temperature, and boom, and it becomes very fluid very quickly, and then it works its way up and punches through. All right, rejuvenated stage volcanism. Submarine to subaerial. Well, I say this because we know that the Ko'olau and the Koko crater rifts, not Ko'olau, the Diamond Head, and the Ko'olau, Diamond Head and Koko crater have vents and what appears to be cinder cones offshore underwater that erupted underwater. So rejuvenated volcanism can happen on the island itself, or it can happen underwater. It doesn't necessarily need to happen above, subaerially. It can happen on the flanks too. So generally occur after a period of about 500,000 years. They're responsible for about less than 3% of the volcano. Some fluid are very fluid, but others are explosive and phreatic, meaning Diamond Head was phreatic and explosive because it encountered groundwater in the reef, in the barrier reef that deformed offshore that it punched through. Often emplaced on coral reefs developed due to the subsidence of the island, greater than 500 meters. Partial melting has reduced significantly. It has now moved to the base of the lithosphere beneath the Pacific Lake, but does not include much of it. Very important. No shallow magma mixing chambers. Mixing is done near base, if any. Conduits do not follow similar ones to shield or post-shield stage, possibly related to decompressional melting as volcano moves off the plume center and erodes, reducing the weight load on the ocean crust. Further uplift associated with the building of new shield volcanoes and development over the hotspot plume. In other words, the newer volcanoes become big, they're heavy, and they will start to flex the crust, and again, helping this occur. As a volcano increases in mass, the ocean crust bends in one area and uplifts in another, simply due to physics and dispersion of mantle material. Evidence of magma mixing. Okay, so there is magma mixing in some of these, and it has a tendency to, that's the $65,000 question. What are we seeing? Where does this happen? Why does this occur? And so we plot radiogenic lead over unradiogenic lead. So I'll read this through this. So KSPD and Hawaiian rejuvenated lavas, these are in the lead isotope. KSPD are main Ko'olau shields, and then we are plotting those, and then Hawaiian rejuvenated lavas. And the rejuvenated lavas are from West Maui, Kauai, and Honolulu, and Kalapapala. Okay? Now, the main shields are right here. So they plot basically on, this is the Loa and the Kea trend, ambient mantle. This is possibly more, sediment-induced old recycled crust. This is old recycled crust mixing in with plume material, and this is ambient mantle mixing in with this is a very well-known trend, and I explained it in the first lecture. So, but we're looking at these compared to the shields and the differences. And the differences in these is telling me, just by looking at this, that the main shield was very much related to the recycled slab materials, whereas the rejuvenated stages have a tendency to be outside of that. And that is telling me that you're getting more depleted mantle put into this. So, dashed line represents the Loa Kea boundary. Ko'olau belongs to a lower trend volcano, yes. And the KSP lavas, the main shields plot on the left and lower side of the Loa Kea boundary. However, rejuvenated lavas from Ko'olau, the Honolulu Volcanics, plot together with rejuvenated lavas of West Maui, East Molokai, and these plot together on the eastern side of the Kea boundary. The rejuvenated Koloa volcanics of the Kauai straddle the Loa Kea boundary, but predominantly plot in the Kea field. So, interesting that these have a tendency to plot over on the Kea side. And what really this is telling me, and it doesn't even say it here, but this is telling me that because the Kea has ambient mantle and has some depleted mantle in it, it is being mixed in with this. So, was there a change in influence of the magmas in the plume towards the end of the Ko'olau? Possibly. But more likely, since all of these seem to plot, it seems to me that you're just getting a more depleted mantle source, and most of the recycled stuff has been gushed out during the main shield stage. That's where I would take that. But these are all, essentially post-erosional volcanics that should be, I believe Kauai is a Loa volcano. Ko'olau's Loa. West Maui might be Kea. East Molokai, it's definitely Kea. So these are the two that you would think would be somewhat, geez, I don't know, I'm not 100% on that. Is Kauai? No, I think these are both Loas. So it makes sense that would here, but it also makes sense that Kauai would be sort of close to it too, because it is a Loa. These are Kea volcanoes. So you do get a sort of a transition towards Kea, but I think it's not so much the source is different from lower Kea. I think it's just Kea just has more ambient mantle in it, and that has a tendency to show up a little bit more as time goes on. You're incorporating a bit more depleted mantle into the melts for the rejuvenated. Rejuvenated stage volcanism in Hawaii refers to a late minor stage of volcanic activity that occurs after the volcano has largely completed its shield building phase and entered a period of dormancy. These eruptions are characterized by low volume, infrequent, and localized activity, often occurring after long periods of erosion and weathering. Examples include Diamond Head on Oahu, and many vents on Oahu. I shouldn't say some, many. A more detailed breakdown. 1. Rejuvenated volcanism. In some cases, renewed volcanic activity. Rejuvenated volcano can occur after a long period of erosion. We know that. These eruptions are typically smaller, less frequent than those during the shield building stage, and they may occur at different locations on the island. Rejuvenated volcanism can add new features such as cinder cones and lava flows. Quartz is replaced by silica undersaturated minerals such as nepheline or melilite. Typical lavas produced are alkalic basalts, nephilites, and melilites. Thought to consist of at least 3 major mixing parental lavas: depleted magma content, which I just said, which is unradiogenic, low strontium. So thought to consist of at least 3 mixing parental lavas. One is depleted content, which is unradiogenic PB, has low strontium and high niobium, and they're EM1 type lavas. 2, this is always screws me up. The second is EMI type, which is unradiogenic lead and niobium, but has radiogenic strontium, meaning that it's old. So the EM are old recycled crust. And then there's a deep radioactive primitive melt of the main shield stage, which ends up sticking to the sides of the plume and causes a reduction of radiogenic lead over time. Remember, during the main shield stage, the deepest part of the core becomes a source. So this is a mouthful, but what it's saying is there's 3 parts. 1, depleted content, which has unradiogenic lead, low strontium, and high niobium. 2, EMI types, which are unradiogenic lead, niobium, but have radiogenic strontium. And then 3, a deep radiogenic primitive melt source that is associated with the main shield stage that accretes onto the side of the plume walls. And as I said, this plume may accrete to the sides of the plume conduit, causing reduction in radiogenic lead over time. Remember, during the main shield stage, the deep part of the core is source. So as they are often related to another shield volcano upstream of the island, basically flexing the crust and allowing decompression or melting. And some islands do not go through this stage at all. All right, I think that makes it more clear. 1, depleted content, unradiogenic lead, low strontium, and high niobium. 2, EMI type, unradiogenic lead and niobium, but high radiogenic strontium, which is old recycled crust. And 3, a deep radiogenic melt of the main shield stage. This plume material may accrete on the sides of the plume conduit and cause the reduction of radiogenic PB over time. So remember that during the main shield, the deepest part of the core becomes the source. And they are also often related to, as I said, another island upstream that's building and then weights down the crust and then bows it out and then flexes the downstream island up. And again, some islands don't even go through this stage. So I hope that makes it a little more clear, because this was where I got confused. All right, rejuvenated volcanism continued. Secondary volcanism at in Hawaii. Secondary volcanism in Hawaii is manifested in 2 forms: offshore rejuvenated eruptions and the Hawaiian arch eruptions. I'm not going to go into this too much because this is something that's sort of outside where I wanted to go with this, and I didn't even know it existed until I started doing this, but it's worth noting. And basically, this is the uplift not only causes it doesn't only just cause flexure in one area. It's a huge bow. It's like putting a bowling ball in a mattress. It's going to flex up around the whole thing. Now, there are areas that aren't even associated with the volcanoes themselves that will sometimes produce rejuvenated volcanism on the ocean floor. And we have one that's up in the northwestern, sort of like northwest of like Oahu and Kauai, or north of it, and then another field that I believe is southwest of the Big Island. And they're fairly big fields. I don't know a lot about them. But anyways, this paper proposes a model in which both types of vol originate from direct sequence of flexural uplift. All right. The uplift causes decompression of the underlying heterogeneous plume material, which first melted partially beneath the shield and has since flowed laterally and is now beneath the arch. In support of the model, this is what this paper is referring to, we have shown that secondary volcanism frequently occurs at locations predicted for the rising flexural arch of active volcanoes. To predict, the predicted magma volume fluxes are comparable to crustal production rates of onshore and offshore secondary volcanoes if magma focuses from broad areas in the mantle to individual eruption sites. The model successfully predicts niobium and strontium isotope observations for a range of lithospheric thickness and plume temperatures, with a mixture of depleted peridotite source and an enriched pyroxenite source. The same parameters also predict mean extensive partial melting that are consistent with alkalic magma generated beneath the arch and thalliatic magma generated in a plume stem. The most important model parameters are lithospheric thickness and mean mantle temperature, Bianco et al., 2005. This is basically saying there are three sources that are contributing to rejuvenated volcanism. You have the mantle source. You have a source that gives you high strontium and niobium isotopes. You have depleted mantle, and then you have an enriched injection that lowers the melting temperature from a pyroxenite source, this is what happens during the main shield stage. You go from peridotite, and then you end up producing pyroxenite in one of the initial melting stages. So that's all this really says, and this is a mouthful. All right, so this is one of the most difficult slides I had interpreting, and I've gone over it. I even wrote some stuff in it, and I hope to God I can make this make sense. But the gist of it is, the main shield, Ko'olau main shield stage. This is the oceanic crust. This is a lithospheric mantle, okay, 100 kilometers. What this is saying is that during the main shield stage, which is right here, you have the melting zone right there, one of them. And you're bringing up peridotite, which is basically, there's more peridotite, but when it goes through this, you get pyroxenite melts, which is the late stage. I'm sorry, you bring up peridotite, you bring up eclogite and peridotite. The peridotite melts and reacts and in this area here and produces pyroxenite melts that fuel the main shield stage. And so there's more of this than there is of the Makapu'u late shield stage. This is main shield stage, this is late shield stage, and then this is rejuvenated stage. Now, once you've moved off into the post-shield stage, and this should say post-shield, it doesn't. Or, I'm sorry, because it isn't a post-shield stage, Ko'olau never went through that, it is a late shield stage, but is a different chemical signature. And in this area, because you're getting mixing or you're getting magma mixing here, you are going to get a pyroxenite melt, because once this comes up and it goes here, you get pyroxenite melts. Which are greater than the peridotite, because the peridotite was more or less used up here. Now you've gone into pyroxenite, and you're generating a pyroxenite melt that is fueling the late stage Makapu'u, late stage shield stage of the Ko'olaus. And then when you come down here, about 300 kilometers for the Honolulu, the rejuvenated, you are getting some peridotite, plus you're getting some of this entrained mantle. This is just, ambient mantle, and you're getting some depleted mantle, and that is somewhat in here. So you're getting three different sources. You're getting the original peridotite that sticks to the side. You're getting the melt up in here that produces the pyroxenite, and you're getting some depleted mantle from here. And that is the best way to explain that. And now the melting here for the main shield stage is different, obviously, than here. And the melting again, I'm going to have to make a little, okay. So I went in and put the the post-shield stage right in here. This is the main shield stage, post-shield stage, rejuvenated stage. Now, this is not exactly to scale. This could be moved around. But this is the basic gist of it. So, one, main shield stage, you got primitive peridotite, which is greater than the peroxenite melts because it's generating peroxenite melts. So you have basically peroxenite melts, which are the early shield stage, which are more abundant than the late shield stage of the Makapu'u. When you go into late shield stage, you've got peroxenite melts, which are now outnumbering the peridotite coming through. So you have more late stage magmas, which is Makapu'u, than you do Kali'i, which makes the late stage cap. And then when you come to rejuvenated stage, you still have peridotite because it got smeared onto the sides of the conduit. You also have entrained mantle, which because the melting zone for rejuvenated stage is below the actual plume itself and is now in somewhat of the entrained mantle. And then of course you also have some depleted mantle. So you've got three different sources here, and that is basically what creates the rejuvenated effect. So it's complicated, but at least we're beginning to understand it. So some ambient entrained mantle, some depleted mantle, and then of course you have some peridotite from the main shield stage that was, basically dragged and kept onto the sides of the mantle plume, which is also dragged down here. So it's probably somewhere in here on the sides of this. So the cartoon illustrating the evolution of the Ko'olau volcano from main shield to late shield and rejuvenated stage from the point of view of potential sources in and around the plume. The diagram shows a schematic cross sections with depth slices through the east-west direction of plate motion is from the right to the left, blah, blah, blah. The overall plume structure consists of a fast swelling upwelling material from the deep plume, bang, surrounded by sheaths of thermally entrained mantle, which is this right here. There's also some of it over here. The plume core is postulated to consist of vertically stretched out mixture of peridotite, eclogite, and peroxenite, which is these right in here. The plume core, and because of all these mixtures of different peridotite, eclogite, and peroxenite, they have different melting temperatures, and it overall, I believe, lowers it. These lithologies correspond respectively to the Kalihi and Makapu'u isotopic components. The isotopic signatures of the Ko'olau main shield stage are mostly derived from melting of the peridotite. Yeah, we know that. The late stage lavas are derived from peroxenite, while the rejuvenated stage, the third stage, are from low degrees of melting of entrained mantle. Importantly, the large degrees of melting involved in shield bending effectively strip the plume core of highly incompatible elements, leaving a barren zone, which is this right here, flowing from right to left beneath the lithosphere. Although the barren zone may contribute to the melts of the Honolulu volcanics, the isotopic signature of the volcanics is mostly derived from materials unmelted during the shield building stage lying outside the plume core. So this core smears the sides, and eventually these sides get, as this gets dragged down, the core goes like this. And right along in this area, you are getting smeared peridotite and stuff right here that also gets, melted as a residual, because this isn't just here. You're going to find it in here and in here, and it ends up basically having residuals right here. So when this melts, you get mantle, depleted mantle, plus this stuff right here. Boom, got it. All right, so this sort of tells you, this graph here tells you that there are three different types of things going on in here. You got the depleted content, which is right up in here. You've got the eclogite component, which is here, and then you have the peridotite component. And it's very simple. Radiogenic. Actually, this one's fairly radiogenic. This is primitive stuff. This is recycled material from old subducted ocean slabs, and this is ambient mantle. Very, very simple. It was very hard for me to go through when I did this, but now I can kind of see it. So when you look at this, it makes perfect sense. This is bringing up recycled crust. Oh, I'm sorry, that's not recycled. This is recycled crust right here. this is primitive stuff. So yes, yeah, that makes perfect sense. And then you have the depleted component right here. And the completed component has, you know, it's got some high niobium. The recycled stuff has, you know, fairly high niobium, but it also has, it's got a little bit more strontium into it, which makes sense because it's mixture. And then when you have the primitive stuff, you've got lower niobium, but yet higher strontium. And the reason for that is, I don't know why that is. And we're not going to go into it because I'll end up confusing myself and getting into the weeds, and we do not want that to happen. But as a rule, yeah, recycled crust, peridotite, and then you have the, yeah, these are the, this is just showing you that these three different things are plotting in separately, so that means that this is consisting of at least three different components. All right, flexural uplift, creating the melt for rejuvenated volcanism. So here's the plume. Everything's firing, it's coming up, it's producing Kilauea right now. As Kilauea grows, it bends down, and then you end up lifting one of the other islands, and in this case it was Ko'olau. And as you did, you allowed this bulge, and guess what? You initiated, you took off just enough pressure to begin to start melting material at the base. And as you do it, the bigger this gets, the more, and the more that this is going to lift, and the more that this erodes, the more this you're going to start producing the melts needed for rejuvenated volcanism, and they're eventually going to punch through. So it's just interesting how you can see that this is directly related to this, and without this, you do not get this. This is the distances. This is a correlation between volcano time between post-shield to actual rejuvenation stage. So, Kauai, right here, we had a hiatus of 1 million years. Ni'iau, we had a hiatus of 2 million years. Ko'olau, we had a hiatus of 1.3. East Molokai, it's 800,000 years, okay. And then West Maui was 0.6, and then Haleakala is still in its post-shield stage, and it has not gone into rejuvenated stage yet. So interesting that, you know, 1 million seems to be about the average time. This one seems a little bit longer, maybe because it had something to do with maybe the volcano just wasn't as big. I mean, Kauai is a really big volcano, so maybe it took longer for it to actually initiate. But in any case, there is a correlation. It takes about, between 500,000 to 2 million in this case for the volcano to go from shield to post-shield to rejuvenation stage. And again, Ko'olau did not go through a post-shield stage. It only went through a late shield stage, which is different. It is not a post-shield volcano. There is no post-shield lavas known on Oahu. It only went from shield stage and then right into rejuvenated stage. All of these had a post-shield stage. In Haleakala, I mean, it looks like it's just about to go into rejuvenated stage. And, finding these, the evidence for these is going to be harder the further back you go in time, because more and more of the volcano was destroyed. So it makes sense that the times are a little bit more constrained here, because the volcano is still standing and we can go out and see it. When you get to these, well, there's a lot of erosion going on, so it makes sense, although Kauai's got a pretty good record. But Ni'iau, there's not been a lot of work done there. And I would say that this may even be smaller, but we may never know, because it's very difficult to figure out the missing evidence if it's not there. You're extrapolating. Ko'olau seems about right. This has been studied extensively, and that's about right. Distance from Kilauea versus stage and time. So I think that's supposed to say age. I don't know why I put stage. But no big deal. We'll let it go. All right, so the gist of this is, oh yeah, it is stage because it's volcanic stage. Okay, so we have Kilauea right here. We got Mauna Kea, Mauna Loa right here. We have Ko'olau. We have Haleakala. We have East Maui. We have all the volcanoes right here, all the way through down to Niihau. And what they're showing here is you see the extrapolated shield stage, which is in this area right here. We have the actual shield stage, and then we have the rejuvenated stage. So we're thinking that these right here all sort of correlate with the major building of the majority of the construction of the Big Island. All these grouped together basically come together to give you a time period for the construction of the Maui Nui, which is Maui and the rest of the islands when they're all connected. And we have Kauai and we have Ko'olau right here. I'm sorry, Waianae and Ko'olau, and then we have Kauai over here. And what they're showing is they're showing the main shield stage. They're not going into the late shield stage or post shield. They're just showing you the shield stages, the main building stages, and then they're showing when rejuvenated volcanism and the time period that it's gone through. So there is, without a doubt, this is about 300 kilometers. There's a correlation between the building of these volcanoes and then the flexural uplift of the Ko'olau volcano on Oahu. And the time and the distance is about 300 kilometers. And if you notice, the same gap is right here. So it's very likely that this initiated this, as well as this initiating this. And if you look, it's the amount of time that this has been going on is from 4 million to close to 1.5. That is a very, very long time for rejuvenated volcanism. And the same thing with Niihau. It's gone on for a couple million years too. And these were the original. These are the original building of these, and there isn't much of a gap here. Huge one here. Waianae never had it. Ko'olau has got a pretty good gap. West Molokai, we don't know that it had any. East Molokai had this right here. Lanai did not have any, and West Maui has had a small series of post-erosion, of rejuvenated, and Haleakala has not gone into it yet. But so this is what we consider the shield stage, but we also are going to go that they are probably, you got to bring them back, a significant amount of time because we just don't see them. So, this gives you an idea of when they've started, and then when they started, when they built, and then what their effect was on downstream islands. And you can clearly see a correlation of about 300 kilometers between the masses of the Big Island and Ko'olau and then the mass of Maui to Kauai. That's what this is showing you. Another confusing diagram, but the way to look at it is you got to look at it over time. So the initial eruptive event of Kauai, I believe that this is Kauai, is here, and then it kind of peaks here, and then it kind of comes down here. But what's interesting is that you're producing different rejuvenated lavas depending on so initially you're getting basonite and fluorite only in the beginning, and then you're getting a little bit of alkali basalt, and then you're getting much more of it during the majority of the building, and then they sort of just become a little bit more even. The reason for this is not entirely clear to me, but if I was going to make a stab at it, I would say that it may have something to do with the source. So quantitative representation of the temporal variation in predicted rates of flexural uplift, i.e. magma flux, from the loading of the Pacific Plate by a new Hawaiian shield volcanism. Again, this is from Bianco. The y-axis indicates relative intensity of predicted melt generation, which is plotted against observed eruption rate based on new and previous renovation ages. Kauai is 500 kilometers from the load focus of Mauna Loa volcano. The Pacific plate is assumed to have moved northwest at a rate of 100 kilometers per million years. Kolau volcano volcanism began 0.3 million years later than expected and continued for about 0.5 million years longer. A histogram of the rock types in the 0 to 5 in 0 to 5 million years. Oldest rocks are strongly alkalic, or are strongly alkalic phyotites and basanites. There are no alkali basalts. A peak in volcanism occurs at the midpoint of the duration of rejuvenated volcanism on Kauai, producing all three rock types. Volcanism apparently decreased markedly on the last million years, although it was not accompanied by an increased percentage of phyotites, shown in boxes. So this is what you initially get, and then you evolve where you get mostly phoidite, or how you pronounce that, and basanite with a little bit of alkali basalt. But then this is basically these are the most samples, or we think that this is sort of the peak. You get a mixture of all three, and then the phoidite, which seems to be the initial, that seems to be the early on, it begins to phase out, and you're left with basanites and alkalic basalts. The reasoning for that is not completely clear to me, although I'm going to go with that this is a deeper source. It may have more iron in it. I think it does. And because of this would be a function of temperature. This would make total sense, because if there's more iron in this, you're only going to get it when it's hot. And if it starts to cool down over time, which it's going to, especially with your percentage of melts, you're going to lose this one first, because the iron is going to start precipitating out of it, and you're going to get more alkali rich. That'd be my guess. All right, the Coco Rift System. Now, this is a picture of Ko'olau. This is the southeast shoreline. This is Coco Crater, Sandy Beach, another favorite place of mine to go. You have Hawaii Kai here, and this was the original shoreline at one point. I've always said there's probably beaches all over this place, but 50, 60,000 years ago, this whole rift opened up, and you've got 1, 2, 3. I would say there's at least 12 to 15 vents right here. I think that might be one too. All close together, all erupted right along this rift, all punching up through what was once a giant barrier reef out here. Absolutely would have been amazing to watch this build. And why so frequent? I mean, these are all fairly, they're not that far apart in age. So this was, something came up and it, made a fairly large rift. And this continues offshore, by the way. So the Coco Rift System is an excellent example of rejuvenated volcanism that occurred, within the last 50 or 60,000 years. It's one of the younger areas of Oahu. Very intensely studied. We don't see really any flows in this. I think there's a lava flow over here. For the most part, this is all phreatic and explosive, so you just don't see a bunch of magmas. But this is Hawaii Kai back here. This is the lagoon. This, everybody kind of hangs out and lives, and fun little area, kind of wealthy. But excellent example of, if you were to try to time these, my guess is this would be the oldest of this area. Then you got one in here, and then one in here. At some point that one came, and then there's one. I mean, it is just a massive amount in a very short period of time. Offshore volcanoes of the Honolulu series, as I said. You can see that here, which is right here. But you see all sorts of other ones that kind of extend out in linear fashion. And then it's the same thing with Diamond Head. You've got a bunch of vents here. You have Diamond Head itself, and then you've got offshore vents all clustered right here. So again, they may not follow the old, they almost are perpendicular to me, like as opposed to, the rift ran like this, but yet all of these are very perpendicular. So that just leads me to believe that when it comes up, it kind of goes like that. Yeah, this just shows you that these can happen underwater, and they do. This is the old reef that's offshore of Hawaii Kai, and it probably went over here, but then this blew up. It's just tons and tons of chunks of reef in these tuffs and ash deposits, just like this too. This one does have a shield right here. It also has a another cone up here that shows a lot of spatter, indicating that these did not come up through a reef through or through water or anything like that. They just oozed out and made actual basalts. Whereas this is, a phreatic explosion. And as a matter of fact, right down here at Black Point, one of these flows came down. It might have even come from here. But so, for one reason or another, when this occurred, there were periods of time where water was not a factor, and that's evidenced by the shield right here, the Kaimuki shield, the spatter cone above it, and then the lava flow of Back Point. Northwestern Hawaiian Islands, main Hawaiian Islands here. Yeah, they're just all atolls now. There's no real. I mean, you do have a couple of rocks that stick up here, La Perouse and what have you. A couple of others, but for the most part, these have all been worn down. And it's interesting to note that there may be. Why is there such a gap right here? This probably has something to do with various plumes from the Hawaii hotspot plume core. Maybe there was a hiatus here, but I mean, when you look at the size of some of these, I mean, some of these islands are real. I mean, this one was just absolutely gigantic. So it looks to me like there was a period of intense activity here, then it slowed down here, and then it's picked up back up here. So these, and over here, there's some islands, but they're not nearly as big, and then they more or less disappear. This is just, these have essentially sunk, but these, I would make a case that the Hawaiian activity is consistent, but it's not entirely consistent, meaning that there's periods where it becomes much. This was definitely an absolute monster of an island, and you can see that they were connected most likely right through here. So you had an island that was probably just like that, maybe even a collapse right here, or maybe a bunch of little volcanoes, I don't know. But these are typical of northwestern Hawaiian Islands, very low, very flat, and mostly consisting of reef. And where do the islands go? This has always been an interesting question. I mean, you see the trend right here, but then you see a huge bend right here. We think this is around 48 million years ago. Why? Why did that happen? For the longest time, these have been getting dragged right up here, and then they were getting dragged under here. I mean, is this an extent of this? It seems weird. I don't know, but for the longest time, stuff was going up under here and getting subducted under here, and now everything is going this way. So the question is, where did this? Was this over here? I mean, you would have to. So it just plays with my mind so much. I mean, but right now these are getting dragged. Well, they're not anymore. They're getting dragged this way. So, I mean, maybe that has something to do with what's going on with all the volcanic activity here over time. I mean, if these were over here at one point, they have been slowly getting dragged under. But now this is eventually going to go this way. So my guess is that maybe this was the primary active rift zone, along here, and then at some point subduction started happening here, and for one reason or another, it just changed the course of the plate being subducted, where this became the dominant direction. But the fact that it's so abrupt has always been confusing. And is this an old arc of some sort, or is there subductions? Something weird is going on right in here. I don't know what it is. And I mean, as this gets dragged this way, I mean, is it possible that this, like, the reason why the gap is here is because it was originally here and then it's been moved off, and so now you're getting a space? I don't know. It's really like I would love to figure out, do we take this and do we bring the plate all the way back here? And so that means it was going up under here? I mean, it's just so confusing. And then over time, if there was really a chain, it would have just been getting dragged under this, periodically. And there would be islands accreted onto here. So you would really need to look and see if there's odd stuff that's been accreted onto these, this subduction zone. But in any case, these are all going this way now. So that's where they're eventually going to go. But it would be interesting to find out if these are related. So it's 42,000 years, 42 million years. All right, so evidence of erosion, subsidence, and accretion. This is just basically giving you some time on the actual older islands. I mean, this is 7 Points is Kauai. So, the older Hawaiian Islands are between, 7 and, probably 27 to 30 million years. Then you become Goyutes, and then you start going up. And that turn happened at about 42 to 45 million years. The oldest ones here are, up here around 64 million. Funny that this is about the time the dinosaurs got whacked. But you can see that there's a bend right here. So, I mean, are these getting accreted here, or are they getting subducted? I don't know. And then, of course, you have a linear trend that goes this way. So this whole thing right here, it's very difficult. So if this is 20 million, 33, it's very strange. I don't even know what to make of this chart. I don't even know why I put it up there. Yeah, I just wanted to look at the distances of the volcanoes, but they're essentially saying that this right here is the same time distance as this, 61, 25. It's very interesting. This is Nahoa Island. This is one of the youngest northwestern islands. It is basically in its last. There's no. It's funny because there's no real barrier reef on this, but believe me, there's a huge platform that this sits on. This looks like a magma chamber to me, and it kind of went out this way. Could have been a chamber that that held magma, and then it had a rift zone or fed an eruption that went this way. There's all sorts of dikes that there's one right here, one right here. These are feeder dikes, but this is what an older Hawaiian island likes before it's about ready to be taken on. That is really interesting. That looks like a giant magma chamber right there. Wherever the center of this was probably this way, so yeah, it could have been. This is Midway Atoll. This is what you look like when you're about 30 million years. I think this one's about 8 to 10. This one's about 30. You got the Midway Runway. You got the lagoon. You got waves. Just pounding the island. And eventually, if the coral cannot keep up, it will eventually get to a point where it goes below the ability to grow, and it sinks and becomes a goyu. And this is going into colder and colder water, and that's eventually what's going to happen. And this is what you would see from this is the view from the surface of the ocean at any Emperor Seamount. Take it in, understand it, get to know it well, and that's what you'd see. Any Emperor Seamount, that's what you're going to look. That's what it looks like from the surface. And this is Bella, and we all know about Bella. Hey, Bella. So anyway, a difficult lecture for me to do. I don't know if this one's any better or not, but I'll take a look at it and see what we think. So should this make it to the screen? Well, I guess I chose it was better. But anyways, thank you for watching. Enjoy the summer coming up, and I look forward to doing the Adirondacks and the Chain of Lakes up in northern Maine lectures that will be coming up in the next couple of months. So aloha.